Okay, let's make a graph. I find that a lot of students have trouble making graphs, so this is some actual real data that I collected, and we're going to make a graph. I'm going to do it at least two ways. I'm going to do this on graph paper, which is the way you should do it first, and then I'll do it on Google Sheets also. I may do it another way if I get excited. It just depends. So let me explain this experiment. The idea here is to take these coffee filters, and if you take this coffee filter and you let it go, there's a downward gravitational force pulling on it. As it falls, there's also an upwards air drag force, FD. And the drag force, the magnitude of the drag force is equal to 1/2 rho A C V squared. So this is the density of air. I'm not going to write it out. Density of air, the cross-sectional area of the coffee filter. This is a drag coefficient that depends on the shape, and that's the velocity. So the important point is that once this thing speeds up, it will reach a constant velocity where the drag force is equal to the weight. So at that point, at terminal, we call that terminal velocity. At terminal velocity, then the following is true. 1/2 rho A C V squared is the upward drag force, and that would have to be equal to the downward weight. So if I find the terminal velocity, V, for a particular coffee filter, and then I use two coffee filters, what happens if I have two coffee filters? Well, the mass changes, but C doesn't change. It's the same shape. The cross-sectional area doesn't change. It's the same size, and the density of air is the same. So I can change this and I'll get a new terminal velocity. So I can do that, and that's what I did. So I dropped one coffee filter, 2, 3, 4, and 5. And I collected, these are actually average terminal velocities. I did it 5 times. Real data. And the mass of each coffee filter is a gram. I picked. It's fine. So the first thing is I want to make a graph. But if I graph, let's say my two variables that are changing are V and M. If I plot V versus M, it's not going to be a straight line, so I don't want to do that. Well, let me think about this. Why do I want to make a graph anyway? Well, the answer is that the graph, if I create a function, I can get a functional relationship between these two. If I can make a linear graph and I get a linear line, then it shows it's true. So let's plot this. Let me solve this for V squared. V squared equals, and I'm going to keep the M out separately, 2G over rho A C M. So if I plot V squared versus M, that is just like Y equals mx plus b. So the vertical axis will be V squared, the horizontal axis will be M, and the slope will be 2G over rho AC. But more importantly, you could do that with each individual data point. I could find the mass, and there's my terminal velocity, and I could solve for it. But it's better to do it all at once. I get all the data, and it's better for uncertainty too, but I'm not going to talk about uncertainty today. So in order to make this graph of V squared versus M, I need the masses, which is easy to get, right? I can just add a column right here, M. This is just going to be 0.01 kilograms, 0.02, and so forth. And then I need to get the velocity squared. So let's do that. So let's square these velocities. I'm going to use, you'd think, hey, this guy's going to use Python. No, I'm going to use this calculator. So I'm going to actually square it. I'm not a big calculator fan, just because I'm not really good at them. So let's do this one. So 1.1756. And yes, there's a lot of digits. Don't worry about significant figures. We don't do that. We use uncertainty, and I'm not doing that today. Squared. Okay, well, how do you do squared? Right there, squared. Enter. Okay, so I'm going to write this down. 1.382. That's plenty of, I don't even need that many. Okay, now clear. I'm really not good with calculators. 1.4888 squared is 2.22. Let's just write it that. And then the next one is clear. 1.8844 squared. I get 3.55 clear. 2.2178 squared equals, I'm getting better with the calculator already, 4.919. And then down here, I get 2.3894 squared, enter. 5.71, let's call it. So I want to graph this VT squared versus the mass. Okay, so let's do that on graph paper. So now we get real, actual graph paper. This is real life graph paper. And I know the squares don't completely show up, but I'm going to move this. I wonder if that works better like that. Or does it work better with a white under it? Let's see. Put this on top of the white. See what that looks like. I wrote something there. Okay, I think that's good enough. Okay, so now here's the first thing that we need to decide when we're making a graph, and that's where our axis is and how big everything is. So let's go back over here. Look at my mass. I'm going to have my mass go from 1 to 5. Okay, so if I go back here and I count, how many squares do I have? Let's just start. Let's say I start right. You can't even see that. Let's say I start right here. Let's just count. 1, let me put a little dot there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. That's 25 right there. Okay, and that's important, right? Because I have 5. I have 0 to 5. So I actually need 5 more. 1, 2, 3, 4, 5. Okay, so I'm going to have enough. So if I put each one of these squares as, each 5 squares as 0.01, then that will work. I want to see, because that's the thing. If I put each square as a gram, then I'd have my graph would be this big. It'd be squished down in there. And there's no reason to squish it down. I have all this paper, so I'm going to go ahead and put this as my x-axis. And so I'm going to say 1, 2, 3, 4, 5. That's going to be 0.001. 1, 2, 3, 4, 5. That's 0.002. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so you see, if you ever do this and you have less than half of the graph, you could always just double the size if you use 2 squares instead of 1, and it would take up twice the space. Okay, so you want to take up as much space in this graph as possible, and you don't want to do this on paper. You have to use graph paper because the size of the squares is very important. So this is going to be 0.003, 0.004, 0.005. Oh, it did count that wrong. And that's 0. And it does not have to start at 0. Okay. In this case, I could start at 1, but it doesn't really matter. And this is m in kilograms. Okay, now for my vertical axis. I'm going from 1 to 5 to 6. That one goes over that. So 1 to 6. So let's just count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I could do that. 16, 17, 18, 19, 20. I'm going to try that. So I'm going to put this at 1. So this is VT squared in meters squared per second squared. And I'm going to say this is 1. And then I'm going to say 1, 2, 3, 4, 5, 2, 1, 2, 3, 4, 5, 3, 2, 1. Did I count that right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So that's going to be 2, 3, 4, 1, 2, 3, 4, 5, 5. 1, 2, 3, 4, 5, 6. Okay, so there's my vertical axis. See? That wasn't so bad. So now I'm just going to literally plot these data points. So I'm going to find 0.01 kilograms on the x on the horizontal axis and 1.382. So we're right here, and then this is 1, this is 2, 3, 4. So 1.38. So this is going to be 2, 4, 6, 8. So this is 1.2, 1.4. So it's almost up to here. So I'm going to put it right there. It's not quite to 1.2. Okay, the next one is 2. That's easy to do. And then 2.22. That's going to be easy. So here's 2, 2.2, 4, 6, 8. So it's a little bit above that. Let's just put it right there. And then the next one's 3 and 3.55. So I'm on this. 3.4 is right here. So it's a little bit about halfway. You see how I'm doing this? Okay. And then 4 is going to be equal to 4.91. So 4.91 is almost up to 5. So there's my 4. So about right there. And then my last one's 5.71. So 5.71. So that's 5.8. So it's a little bit below that. So right there. And then I go up from 5. So about right there. Okay, so there's my 1, 2, 3, 4, 5 data points. Okay, now 1, we're already kind of winning. That does look linear. But the next thing I'm going to do is I'm going to add a best fit line. Now this is a best fit line that I'm going to add just by estimating. So I'm going to take a straight edge like this, and I'm going to try to make it so that it comes as close to as many of these data points as possible. You don't want to just take the first data point and then draw a line to the last data point, because that ignores all the data points in the middle. So instead, I'm going to take this, and I don't have to touch any of them. I'm going to try this line right here. I'm pretty happy with that. I actually didn't even touch any of them. Okay. And so there is some uncertainty associated with this, and that is fine. Now what I want to do is find the slope. So let's just call it the slope. So how do I find the slope of this? The first thing I want to do is to pick 2 data points on the line that I drew, not actual data points. If I do, again, I'm just using those 2 data points and ignoring everything else. I'm going to look for places where this crosses exactly or close to. That one's pretty close. I come down here. I want them far apart, and I want to pick ones that are easy to get. Okay, I'm going to have to just approximate here. Not easy. I'm going to go with, I don't know. Let's pick this right here. And then up here, I'm going to pick, that one looks good. Okay. So now I need the x and y coordinate of this. So its x coordinate is going to be 0.1 or 1. And this is 1, 2, 3, 4, 5. So this is 2. So this is going to be 1.0012. And then that one's 4. So it's a little bit less than that. So this is going to be 0.0012. 2. I'm just guessing there. Okay, now for the vertical component, it's going to be 1.8. Now for this one, it's easier. The mass is actually going to be equal to, that's 0.0048. 0.0048. And then this is going to be equal to 5.4. So the slope is going to be equal to the change in the vertical divided by the change in the horizontal. So that's going to be 5.4, the change in the vertical, 5.4 minus 1.8, all of that over the change in from here to there. So that's going to be 0.0048 minus 0.00122. And this is in meters squared per second squared, and this is in kilograms. I mean, the slope does have units. So let's do this on, again, not great with calculators. So this is going to be 5.4. I should put it in parentheses. So they have parentheses. 5.4 minus 1. We didn't have parentheses in calculators when I was growing up. Okay, we had to just write down every step. Divided by 0.0048 minus 0.00122 equals. And I get slope equals 1005.59, and this is going to be meters squared, kilograms per second squared. And then I could set that equal to, what did I say? It was 2g over rho AC, and if I wanted to, and I know, if I know g is 9.8, the density of air is 1.2, I could either measure the area of the coffee filter, or I could just use AC and find those together and not even care about it. But either way, that's how you do that. Okay, so now we're going to redo this whole thing, but now we're going to do it in Google Sheets. Okay, so let's go over to Google Sheets. I'll meet you over there. Come on with me. See, here we are. Okay, so I've already got this set up. I've already got the numbers in Google Sheets. Let me make this a little bit bigger. Oops. How do you make this bigger? View, increase, zoom in. I thought that was right. Let's zoom in one more time. Okay. That's not too big. And got it. I don't know what it was trying to... Okay, so there's my data. Now, the first thing I need to do is to actually get my new data. I need to get the mass. So let's just go over here and insert a column. The nice thing about this spreadsheet, I'm not a huge spreadsheet fan either, but the nice thing about spreadsheets is you can calculate the data too before you plot it. So I'm going to insert a column to the left. I'm going to call that M in kilograms, and it's just going to be equal to this times 0.001. And then it says, hey, do you want me to finish? And yes, I do. Okay, now I'm going to insert another one to the left. And I'm going to call this VT squared in, I don't know why I can't see, in meters squared per second squared. And it's going to be equal to this cell squared. So in Python, I mean in every spreadsheet that I know of, if you start entering a cell with equals, you can type a formula and make a calculation. And you can see I get the same values I did by hand, but now I have them here. So the next thing I do is I want to make a graph. So I'm going to highlight this stuff. And you actually don't need the title up there, but I did anyway. Go up to Insert and go to Chart. Now it's going to say, hey, it did it as an XY scatter already. That's strange. It didn't do it the last time. Okay, so if it doesn't, it's just smart enough for me. It may come up with like a line graph. You don't want that. You do not want a line chart. You do not want a bar chart. You want an XY scatter. Okay. So, and it already put in the labels on here, but let me show you how you would get that. If I go to Customize and I go to Chart Title, I can type that in there, and let's say terminal velocity coffee filters. I don't know. And then I can change that to the horizontal axis, and that's fine, VT squared. And then the vertical axis, it has these backwards, right? So I want to go back to setup, and down here, switch rows. No, I don't want to do that. I want to do VT data range. I always get this backwards. So if I just do this can I just do this as B1 to B6, another one? B1 to B6, and then do this as C1 to C6. It didn't do it. X-axis. Okay, let's do that. X-axis is going to be equal to the x-axis. See, what was my x-axis? I want to put my x-axis is B. No. Yeah, B. I want B as my x-axis. So x-axis is B. Okay, and then my y-axis is C. That's better. But now my labels are wrong. So let's go back over here to customize. Vertical axis is going to be VT squared. And then my horizontal axis is going to be M. Okay, so there's my graph. And this is pretty easy. You see that's a pretty easy graph to make. And it did all the scaling for me. It did all of that stuff for me. But you got to be careful, because if you don't know what's going on here, if you don't know how to make it on graph paper, and you jump over here, it may just be magic, right? And you don't want the computer to be doing magic. You want to have it do the stuff that you don't want to do, but not the stuff you don't know how to do. That's why it's important to make a graph. Okay, so now let's add a linear fit. In most spreadsheets, this is called a trend line. Let's see, customize. Legend series, where is it at? There it is. So if I go down here to trend line, it will add a best fit line. I want to go down here to label and say use equation. And you can show R squared if you want to. Okay, so this gives me the slope right there. It gives me a slope of 1136. And what did I have before? I had a slope of 1000. So it's very close, right? The two values are very close. And I'm pretty happy about that, because I just did that on graph paper. It wasn't perfect. The R squared term tells you how close it is to fitting in a perfect line. But there you go. That's how you would do this in Google Sheets. If you use Excel, it's very similar. But both of these methods, it's important that we're plotting a linear function, because we know how to do a linear function, right? If you try to plot a quadratic function, it's not gonna, you can't fit an equation to it. There are ways to do it, but if you don't understand that yet, you need to understand this way first. Okay, so there you go. There's a graph on paper, on a spreadsheet, and why you need to make that. I hope that helps.